Hello and welcome to our third presentation in a series highlighting different facets of technologies that are underway here at the Oak Ridge National Lab. I am Alex Detrana. I'm a commercialization manager. I will be joined shortly by Muralidharan and Yuki Yamamoto to talk about some work that they've been doing in cast alumina-forming Austenitic stainless steels. But first, I'm going to give you this address that you can text or email any questions that you might have during the course of the presentation, and we will address all of those, or as many as we have time for, at the conclusion of the presentation. I'm going to talk briefly about some of the general aspects of the lab, and also a little bit more specifically about some of the projects that are ongoing here at ORNL. First, I want to cover some of the ways that we have for collaborating and cooperating with industry. Moving from left to right on this slide, we've got cooperative R&D agreements, or as we call them, CRADAs. Those tend to be fairly involved, longer-term programs. And then next are technology license agreements, whereby we enter into an agreement with a commercial company which agrees to commercialize the technology. And we've also got work for others agreements, which are essentially work for hire, where you work with our research staff to identify a project and a specific capability that we have here at ORNL that our researchers carry out for you. And then we've also got a series of defined user facilities, which you can often use at no cost. And there are additional details on each of these on the ORNL Partnerships website and also on the ORNL YouTube page. The previous presentations in this series go into greater depth, but I want to focus a little bit on the technology licenses, because that's one of the key reasons for this presentation, is to highlight one of the high potential technologies that some of the researchers have been working on that we want to ensure that interested parties learn about and begin the conversation around bringing that technology to market. I'm not going to cover all the details of this, but I put this slide up just to point out that we've got a diverse portfolio of over 800 inventions divided into a number of focus areas, and the specific ones that I'm going to be talking a little bit about are those in materials and also chemicals. The Material Science and Technology Division is the division in which the researchers you're about to hear from reside. It's got about an $85 million annual budget. It's got a pretty large staff for being one division, and those are divided into 16 research groups. And they do a lot of applied research, but also basic research in structural and functional materials. And it's a very prolific group of researchers with 76 R&D 100 awards, about 60 invention disclosures a year, and about 30 patents that are filed or issued each year. Some of the areas that the Material Science and Research Division are working in, we refer to as transient field processing. That could be pulse thermal processing or magnetic field processing, as well as e-beam processing and laser processing. So a lot of the work that's done is focused on new manufacturing breakthrough kinds of developments. And along those lines, friction stir welding and additive manufacturing are a couple of key areas of focus, and I'm going to talk a little bit in a moment about additive manufacturing as well. This gives you a little bit of an idea of what some of the material focuses are from this research group. Everything as diverse as advanced concretes and carbon-based materials and carbon fibers, to battery materials and high-performance alloys and different types of coatings. And I'm moving through these fairly quickly in the interest of time, but this presentation is going to be posted on the web, and you can review this at your leisure. Carbon fiber is one key area of focus here at ORNL, and the goal behind this program is to get carbon fiber to be used in high volume automotive manufacture. Carbon fibers have been found on fairly low volume automobiles for quite some time, but our goal is to see cars become lighter weight and therefore more fuel efficient. And the research group has tackled this problem by taking a very holistic approach. In the bottom left corner of this slide, you can see the major cost elements that go into carbon fiber. And the first one is basically the precursor material itself. That's just the material cost. And the subsequent 4 items are all processing based. So the approach that this research group has taken is to try to develop new precursor materials in addition to new processes. So the efforts that they have in the area of low-cost precursors is that moving from the typical pan that is used, pan is polyacrylonitrile, focusing on textile pan or melt spun pan and eliminating the solution-based processing, but also looking at alternate materials such as lignin and polyolefin. And then on the processing side, they've focused on the processing steps that are very energy and time intensive, and develops new, less energy intensive and much faster processing steps, such as plasma oxidation and microwave-assisted plasma carbonization. As I mentioned, additive manufacturing is another key thrust area, and the purpose behind this is to enable manufacturing of materials that would not otherwise be able to be made. The hand, the prosthetic hand that you see here was made via additive manufacturing, and an integral in that component are different hydraulic channels that allow all the digits to be actuated, and those are things that either could not be made or would be extremely expensive to be made. And the goal behind this is the fundamental goal behind the additive manufacturing thrust is to enable the manufacture of items that would not be able to be made otherwise, but also to enable additive manufacturing to be used for structural applications. As I mentioned, this presentation and links to this video will be found on the partnerships webpage, and you can also learn a lot more about a lot of other areas at the lab. And the schedule for subsequent presentations is here. We've got another one coming up in about 3 weeks, and you can register for future webinars at the address found at the bottom of this page. So, as I mentioned, please email or text questions to the address at the bottom of this slide. And I am now going to turn the presentation over to Muralidharan.
Thank you. Good afternoon. Thank you very much for attending this webinar. My name is Muralidharan, and my colleague Yuki Yamamoto is here to answer questions along with me here. So what we're going to talk to you about today is a new class of alloys that Oak Ridge National Lab has been working on for a few years. And within the series of alloys, the cast alumina-forming austenitic, the cast alloys are being patented recently, and I'm going to talk to you about its properties. I'm going to introduce you to some of its properties and potential applications as we see possible. So let me just start with a brief description of the technology. What we're talking about is a new class of corrosion-resistant alloys, and these alloys are designed for high temperature use in corrosive environments. On the left, I show here a piece of material, cast alumina-forming alloy, that has been exposed to a temperature of 800 C for 5,000 hours in an air plus 10% water vapor environment. On the right-hand side is a cast iron subject to the same conditions, and you can see the difference in the surface quality after the exposure. So clearly these alloys are able to resist the environment containing water vapor and or sulfur. So what is the design philosophy? The design philosophy in these alloys are to form a stable alumina layer, it's an Al2O3, which is actually shown here in the alumina-forming alloys. You're seeing is an aluminum-rich scale. This is in contrast. It's actually, you can see that marked here. This is in contrast to a Chromia-forming alloy, where the Cr2O3, the chromia, is the primary oxide layer that protects the alloy from its environment. So what is the advantages? What are the advantages of having an stable alumina forming alloy? These alloys really show lower corrosion rates, and you don't have to take my word, and we'll show you the data, and you can make a decision for yourself. Because of the lower corrosion rate, they have longer component life, and then we're able to have a longer duty cycle, and of course the high temperature capability, since alumina is much stable to much higher temperatures. So what are the kinds of components that we are targeting these alloys? Here are a few components that actually are used, for example, in the furnaces, furnace rolls. These are actually cast components that are cast into desirable. I mean, these are components that are cast into desirable shapes and then probably welded afterwards. And here are two examples. As a furnace roll, we thank Duraloy for providing these pictures. And here's reformer tubes used for chemical processing. And at the other extreme, these are of course industrial environments. On the other extreme, we also have high temperature corrosive environments and exhaust manifolds. And the temperatures, as I will show you later, are a little bit lower, but they're also subject to similar water vapor and sulfur containing environments. So why suddenly do we need these alumina-forming alloys? Here's a kind of a brief perspective on why we need these new alloys. Of course, the traditional cast Chromia-forming austenitic stainless steels are already in vogue, and they're widely used. And of course, in exhaust manifolds, for example, cast irons are used. But as I show you in the right, there are two major drivers for the requirements for the new alloys. One is generally increase the demand for improved energy efficiency. Here is an example of the future standards for gasoline fuel efficiency. For example, the CAFA standard demands, it's 34 miles per gallon average in 2016 to a 54 mile per gallon in 2025. So this would imply that one of the methods that many auto manufacturers are adopting is just to keep more heat in the exhaust gas, which means that all the components that are subject to the exhaust gas are now subject to further increased corrosion rates. And that's driven from the automotive side. From the energy efficiency side in the industrial processes, again, there is a demand to decrease energy costs, increase productivity, and reduce downtime, which demands materials that have much better lifetime, and so that there is a due return on investment in terms of cost. So we have three broad classes of alloys that we are working on, and these are kind of targeted at specific property requirements that we are aware of in those classes of components that we are targeting it for. And so here, I mean, I've just briefly summarized this in this table here. We have carbide-strengthened cast alumina-forming alloys that are primarily top off at about 800 to 850 C in terms of temperature of applications. These are covered by US patent, shown here, issued US patents. And the form we think that these will be used in is a centrifugal cast tubes. Of course, these are furnace hardware, furnace rolls, and of course, traditionally they are dominated by the Chromia-forming cast austenitic stainless steels. And the second class of alloys that we have are relatively higher in strength than the HK and the HP type of alloys. They have much higher strength, and they have a much sharper drop-off in strength above these temperatures. So there's a hard limit as to temperature, maybe about 900 C. It's probably the maximum that you would be able to use these alloys. We have a US patent pending application on these. Again, it could be used in centrifugal cast tubes and or shaped components. What we anticipate is these would be used in exhaust manifolds and other hardware that would operate in exhaust streams, but at relatively lower temperatures in the 800 to 900 C range. And we could foresee them replacing cast irons, high CMO cast iron, for example. The D5S, which is a high nickel version of cast, it's a cast austenitic steel, but it's a cast iron. And of course, many manufacturers are even going towards cast austenitic stainless steels or even rod forms, simply to withstand the higher temperatures and corrosive environments. The third class of alloys that we really are aiming towards the ethylene cracking and radial burner tube applications, which is the temperatures are approaching about 1100 C, and where we are still, we have found that, as I will show you later, that we have identified some alloy compositions within the granted US patent application, the granted US patent, that would be able to perform at these temperatures. And these again would be pitted against the Chromia-forming cast austenitic stainless steel such as HK and HP and HN and so on. So what led to this patent application is, I just show you very quickly some of the lab scale experiments that we have done that led to this patent application. Here is an example of the laboratory scale tests done, oxidation tests done on early versions or actually versions of lab scale versions of the cast AFA alloys. And you can see that on the y-axis what you're looking at is the oxidation mass change normalized with the surface area, that is how much milligram per centimeter squared, as a function of 100-hour exposure cycles. And this is the total life. This is like 5,000 hours. And you can tell that the AFA alloys retain a very low mass change, whereas the HK and the HP alloys, for example, start shedding a lot of the oxide, and there's significant mass loss. On the creep side, again, these are experiments done at 750 C at 100 megapascals, and you can see that the HK alloy lifetime would be somewhere here, a couple of 100 hours perhaps, and we have lifetimes going up to 10,000 hours under similar conditions. So the alloys not only have good oxidation resistance, but also have good creep resistance, as outlined here. So based upon these alloys, we worked with Duraloy, who were able to centrifugally cast two alloy compositions that we down selected. And they're all about 45 to 50 iron, about 14 chromium, maybe the 25 to 35 nickel, and of course about 2.5 to 2.7 to 3.5 aluminum, some niobium 1 to 2.5, about 1 to 3, and titanium in the DAFA 30. Is to remember that the primary strengthening phase in the DAFA 30 is the gamma prime, whereas the primary strengthening phase in the carbide in the CAFA 7 is the carbide phase, and so that really is reflected in the fact that we have more titanium and more niobium in the DAFA 30, and of course similar levels of aluminum. So what have we done with what I'm going to show you here is a brief synopsis of some of these results, but we have completed tests on the thermal physical properties, thermal expansion coefficients, thermal conductivity, and so on. We have tensile properties ranging up from room temperature up to 950. We have oxidation resistance up to 900, and as I'll show you in some cases up to 1100 C. And we are in the process of collecting the creep resistance data in air. We have targeted up to a maximum lifetime of about 10,000 hours rupture time. So the first set of data you see here is the oxidation resistance as a function of temperature in the environment of the 10% water air, 10% water vapor environment. And what we compare here is the mass change, and there are several alloys here, and let me just walk you through these alloys. For example, the CAFA 7 is an alumina-former, and the CAFA 7 and DAFA 30 are alumina-formers, and alloy 224 is a high nickel alumina-forming alloy. And as you can tell, these alloys keep a very low mass change as a function of time when compared to the HK and the HP alloys that really have lost significantly, has shown significant loss in mass, which is related to the spalling. On the right-hand side, you're seeing the 800C data, where it's just these effects are magnified. Now, as you can tell, that the DAFA 30, which is the gamma prime strengthened alloy, performs better than the other alloys, probably performs the best within this time scale. And with CAFA 7 and the alumina-forming nickel-based alloys keeping very close track of each other. So really what we have, what this already demonstrates is the potential offered by the alumina-former in terms of providing good oxidation resistance. Now going up to 900C, we show data in dry air that is devoid of water vapor. Now you start seeing some more differentiation. The grade HP alloy, as you can see here, performs the worst amongst these group of alloys. Again, the CAFA 7 and the DAFA 30, the alumina-forming alloys developed by Oak Ridge do good. And probably the best to target for is the alloy 224 under these circumstances, under these conditions. What we also show here is a lab scale version of one of our alloys within the patent that starts to almost track the high nickel alloy. And this we call the HD CAFA 4, and this is the alloy that really holds a lot of promise for the higher temperature applications. And I'll show you at 1100C, this even is better exemplified. What we are showing here is the oxidation mass change as a function of, again, the time at 1100C. And the nickel aluminides actually don't do as good as the alloy 224, which is, again, I just want to show you that it's got about 48 nickel and 3.8 aluminum and some iron and chromium, which is actually a nickel-based wrought alumina-forming alloy. And the HD CAFA 4, which is an ORNL cast aluminum alloy, which is also alumina-former. And you can see how these two are tracking each other very well up to about 1,000 hours. And what is actually shown here is an alloy 230, which is also a high nickel alloy, but it is a Chromia-former. So clearly, again, the alumina-forming alloys come up on top with the good performance of the HD CAFA 4 at temperatures up to 1100C. So clearly, we have shown you the data that illustrates the potential for oxidation resistance in these groups of alloys. And the following, I'm just going to quickly run through some of the mechanical property data we have. What I'm showing you here is the modulus, elastic modulus, as a function of temperature for these two alloys, CAFA 7 and DAFA 30. And you can see that the HK alloy is actually slightly has a lower modulus, and if you're familiar with that from the data book, it seems the HN and the HP actually even are much lower than these alloys. So if you are targeting applications that would traditionally use HK, this would be a good drop-in substitute for some of these alloys, but with the advantage of improved oxidation resistance. So in terms of the strength, here's the strength of the here's the data showing the strength of these alloys at 3 different temperatures. As you can see, the DAFA 30 is really aimed at is a very, very high strength alloy, and it's at least about double the yield strength of the other austenitic stainless steels that we show here. CAFA 7 does well. And it's at least comparable, maybe slightly lower at room temperature than HK, but definitely better than the HN and the HP. As you bump up in temperature, of course, all the strength levels drop. The highest here is 60 KSI, for example. Excuse me. And you can still see that the CAFA 7 is starting to assert itself again, and the DAFA 30 definitely has much better strength properties at 800C. And going up to 950C, the CAFA 7 really starts to hold its own, and this illustrates, and as you can see, the DAFA 30 is now significantly dropped in strength, and this is directly related to the fact that the strengthening precipitate is disappearing at these higher temperatures. So in terms of strength, in the DAFA 30, we are limited to temperatures about 900 or so, which is also consistent with this oxidation performance. So we have also accumulating creep data. We are still in the process of having more tests added to this as we speak. But what we show here is the Larsen-Miller plot for DAFA 30, and also superposed on that is the HN and the HK data. And you can see that the DAFA 30 performs comparable or better than the HK. Temperatures up to about 800 C. Again, remember that the temperatures above 800, 900, close to 900, the strength is going to drop off pretty rapidly. The CAFA 7, with the tests running between about 650 to 950 C so far. Here is the Larsen-Miller plot, and this data point that's shown with an arrow is an ongoing test with an anticipated lifetime of about 10,000 hours. But as you can see, that it is performing comparable to the HN at these temperature ranges. So here is a kind of a brief summary of where we see the advantages of these alloys. The ORNL alloys have good oxidation resistance, good creep resistance, are castable, weldable, and in terms of and they can operate up to 1100 C. And in terms of the cost, we kind of for comparison, we have a few broad sets of alloys here. The primary competition in some of these applications is the cast Chromia-forming alloys, and of course the ORNL technology wins through its improved oxidation resistance. And in terms of competing with the nickel-based alloys, as you can see on the right-hand side here, the cost is a big benefit as far as our alloys are concerned. And as I showed you in a couple of plots, the oxidation performance is comparable at the temperatures we have tested with some of the higher nickel alloys, which is very encouraging from the perspective of applications. Of course, in terms of cast iron, in the exhaust manifold, of course, we have much better oxidation resistance and creep resistance, with the castability of cast iron and the cost being the favored things for cast iron. Of course, this higher temperature operation is very limited. So we presented some of these results at the SAE meeting, and we did receive a good response showing some of the we were appreciated for the benefits of the cast AFA alloys as it pertains to the exhaust manifold application. And in summary, I just shown you that we have developed cast alumina-forming stainless steels, austenitic stainless steels, with good oxidation and creep resistance at temperatures up to 800, 850, pushing up to 900 in air, without 800, 850 in water vapor containing environments, and probably pushing up to 900 in air, dry air. We have alloy tubes that have been prepared successfully using centrifugal casting, and the work has also highlighted some of the advantages of alloys that can be pushed to the 1100 C, and we're really looking forward to working with industrial partners who would be willing to license it and move these alloys out to end user applications. And if you have any questions, we are available for comment right now, and if you have any questions in the future, you are welcome to contact us. With that, I thank you very much for your attention.
Thank you. We now will take questions that have been texted or emailed to us, and we'd like to thank everyone for submitting these questions. The first question we received was, how do these alloys compare in cost to HK or HN alloys?
If you look at the composition of the alloys, let me just go back to that slide. Let me go back to the slide here. The nickel contents is around 25 to 35%, which is right in the ballpark of these alloys. And so, since we have already demonstrated that they are castable, I think the cost would be comparable.
Thank you. Another question that we received during your talk is, have you experimented with weldability of these alloys?
That's a good question. I didn't have time. Let me just show you quickly. We were able to weld Yuki, do you want to say anything? These alloys in the centrifugal, we actually prepared from these pieces were prepared from the centrifugally cast alloys, and we were able to weld using traditional processing. Thank you.
Great. One more question, and it'll probably be our final one to consider time, is what do you have planned for next steps?
So in terms of the next steps, what we're hoping to do is we're in the process of preparing a data sheet that contains all the properties of these alloys, and that would be available for public view probably within the week, within a 1 to 2 week period. And so we really would welcome you to take a look at the data and evaluate it for your application. And hopefully within that you'll find that there's a significant benefit to using these alloys for your and your customers' needs, hopefully. And we look forward to finding some potential partners who will be willing to license this technology. And in the future, we hope that the industrial partner would be willing to work with us. And a few steps in that process would be for example, we identified the HD CAFA 4, which has excellent performance reaching up to 1100 C. So we plan to work with the industrial partner to make these alloys in a centrifugal cast form, test its properties, and then move it on to potential sales and benefit for both application-wise and marketably. Thank you.
Thank you very much. That concludes our webinar for today, and we appreciate your attendance.